right, let's consider the following chemical reaction where we have carbon monoxide gas plus 3 molecules of H2 gas and this yields in an equilibrium process a molecule of methane gas, that's CH4, and a molecule of water vapor, that's H2O. You should be able to look at a balanced chemical reaction and make some thermodynamic assessments. So the first one I think that we should begin with is delta S. We should be able to look at a balanced chemical reaction and make a determination whether delta S is greater than 0 or less than 0. We know that the entropy increases for a given substance as it moves from a solid to a liquid to a gas. So let's imagine that we have copper, for instance. In the in the solid phase, the copper atoms are very close together. They're obviously more dense. And they don't have a lot of molecular motion other than very slight vibrations. Remember, molecules have 3 different ways in which motion can be detected. One is a vibration. And that's when you have 2 atoms that are near each other. You could use the analogy of 2 masses connected by a spring. And then, of course, you can stretch the spring, and you can also compress the spring. So vibration is very slight when you're in the solid phase, and that's the only motion that you have. You can also have rotation. This is when an atom or molecule can rotate about its axis. In other words, you might observe atomic spinning, clockwise or counterclockwise. There's no rotation observed in the solid phase. Finally, there's translation. Translation is probably the motion we're most familiar with. It's really just moving from point A to point B. So if I have an atom at point A and that atom moves to point B, that atom has translated from A to B. There is no rotation, there is no translation for any element, atom, or molecule in the solid phase and also in the liquid phase. The biggest difference between the liquid phase and the solid phase for most substances is that there's a little bit more space between them, so the vibrations are a little bit more pronounced. So I have increased vibrations, and not significantly increased vibrations, just a little bit more. In a gas, however, each individual copper atom would be capable of all 3 types of movement, because I don't have intermolecular forces constraining the movement. So the more IMF you have, the less freedom you have. So delta S increases a little bit from solid to liquid, but a whole lot from liquid to gas. So when we look at a balanced chemical reaction, we want to consider how many moles of gas I have in products, how many moles of gas I have in reactants. If I have more in products than I do in reactants, then the delta S is greater than 0. If I have more moles of gas in reactants than I do in products, then the delta S for that conversion is less than 0. If the number of moles of gas are the same, then delta S is very close to 1. It could be slightly positive, it could be slightly negative. When we look at this balanced chemical reaction, I have 2 moles of gas in products, I have 4 moles of gas in reactants. This delta S will be less than 0. So the first assessment that we can definitively make for this equation is that the delta S is less than 0. One of the most important equations of thermodynamics is the calculation of delta G. We know that the delta G of a reaction is equal to the delta H of the reaction minus T delta S of the reaction. Now, delta H and delta S have 4 different combinations that are possible. One combination is that both the delta H and the delta S are positive. Another possible combination is that the delta H is positive, but the delta S is negative. A third possibility is that the delta H is negative, but the delta S is positive. And of course, the last possibility is that both delta H and delta S are negative. Now, we're not dealing with magnitudes here. We don't know what the actual mathematical values of delta H and delta S are. But in each of these reactions, if I can have a negative delta G, what conditions of temperature would I need? So if we look at the first, if delta H is positive and delta S is positive, if this term, T delta S, is really positive and thus negative, the negative part overcomes the positive part. So at very high temperatures, delta G can be negative. Let's look at condition 4. Delta H is negative, delta S is negative. At very high temperatures, this would be a positive and it would make this positive. So I need low temperatures when both signs are negative to ensure a negative delta G. There is no temperature that would make the second set of conditions give me a negative delta G. If I have a positive number and I subtract a negative number from it, it becomes more positive. So no temperature is possible to make the second condition spontaneous. Conversely, when delta H is negative and delta S is positive, it is going to be spontaneous at all temperatures. Now, I think it's appropriate at this point to talk about driving forces for chemical reactions. There are 2, and they are really important. So this answers the question, why does a chemical reaction occur? And there are 2 possible explanations, which really eventually decomposes to one possible explanation. We know that chemical phenomena will occur when, one, we minimize the energy. Now, the state function that we most closely associate with energy is delta H, which technically is enthalpy. When the enthalpy change is negative, I have minimized the energy. So we want a delta H that is less than 0. We call these reactions exothermic. The second driving force is maximizing the entropy. Most people think of entropy as a measure of disorder. That's really got a lot of problems. Of course, we know that entropy is delta S, and delta S should increase in a system. So when delta H is negative and when delta S is positive, we say that both driving forces for a chemical reaction are present. I want you to notice that when both driving forces are present, we're describing the third condition, the reaction will always be spontaneous. That doesn't tell us anything about speed. It tells us that we will have a greater than 50% conversion of reactant to product. I want you to notice something else. If neither of these two driving forces are present, that is, if delta H is positive and delta S is negative, there are no conditions of temperature that will make the reaction spontaneous. And I think it's very important that you understand spontaneous does not mean the reaction does not proceed. It means that I will convert less than 50% of my original reactants to products. So if I were to look at the conversion of reactant to product and I were to take the amount that's left over after the reaction reaches equilibrium relative to how much I started with, I would have more than 50% left if I had a non-spontaneous reaction. I would have less than 50% left if I had a spontaneous reaction. So no temperature means 0 driving forces. Two driving forces. The first set of conditions and the second set of conditions are the same. Exactly one driving force is present. In the first condition, that driving force that's present is increasing systemic entropy. In the fourth set of conditions, it is the fact that it is an exothermic reaction. Notice that when one driving force is present, the temperature will dictate whether it's spontaneous or not. Now let's go back up to our original problem. We said that delta S is less than 0. That is a determination we were able to make without knowing magnitudes. If we go to our sign chart now, we see delta S is negative in the second condition and in the fourth condition. But the second condition will not result in a spontaneous reaction. Therefore, I can now make an educated assessment of what is happening to delta H. In this case, delta H is also negative. Once I know that delta H is negative, there are a couple of things that I automatically know. So I'm going to simply rewrite the equation. Now these are all gases, so just to be brief, I'm not going to write the superscript G, the subscript G. They're there, I'm just doing that to not waste time. Once I know that delta H is less than 0, I know the reaction is exothermic. I know that the temperature of the solvent, remember, delta H tells us what's happening with the system, with the bonds. The bonds are releasing energy. So the temperature of the bonds or of the system should go down. We can't measure that. We measure the surroundings. We measure the solvent. In an exothermic reaction, if we measure the temperature of the solvent, it will most assuredly go up. This also means that heat is a chemical product, which is very important for doing a Le Chatelier's principle assessment of what happens when I begin changing temperatures. For example, if I increase temperature in an exothermic reaction, I am increasing the concentration of heat. That is the stress. Increase heat. How do I offset the stress? I do the opposite of the stress. So to offset the stress, I simply will want to lower the heat. What's the mechanism in the chemical reaction to achieve lowering of heat? I favor the side where heat is not present. In the case of an exothermic reaction, it will favor reactants. We call this a shift to the left. We could also call it reactant favored. These types of questions are pretty common on standardized exams. Now, that means if I want to obtain more product, I do not want to increase the temperature. Rather, I would want to decrease the temperature. Decreasing the temperature would decrease the concentration of heat. To offset that, I would want to increase the concentration of heat. The mechanism for doing that is favoring the side of the reaction that has heat. So there would be a shift to the right, or it would be product favored. So that's how we deal with Le Chatelier's principle in terms of temperatures. Where it shifts is dependent upon whether it is an exothermic reaction or an endothermic reaction. Now, there is an equilibrium constant that governs this reaction. The mathematical value of the equilibrium constant will only change when the temperature changes. The equilibrium constant value will go down for an exothermic reaction because, again, you favor reactants. And what we need to remember is that K is the concentration of products, which would be, in this case, the concentration of CH4 times the concentration of water vapor. Remember, liquid water wouldn't go into an equilibrium expression, but water vapor can go into an equilibrium expression, divided by the concentration of CO divided by the concentration of H2 to the third power. Remember, the stoichiometric coefficients become the exponents. If I have an exothermic reaction, this shifts to the left, which means the things in the denominator go up while the things in the numerator go down. This will cause the value for K to go down. So this is how we can relate finding delta S, delta H, determining if it's exothermic or endothermic. What happens, of course we want to decide if heat is a reactant or a product. What happens if I increase the temperature or if I decrease the temperature? So just as some added practice, I would like for you to go through the same assessment for two reactions. Now look, we aren't always going to be able to find everything that I have listed here. Part of your job is to find the limit of the knowledge that you can determine. So I'm going to give you two reactions and I want you to practice this, and then we will go over those solutions later. One would be N2 gas plus 3H2 gas yields 2 NH3 gas. This is one example. The other example I want you to attempt, let's do this reaction. Let's do 2KClO3 solid breaking down to 2KCl solid plus 3O2, and that is a gas. So I want you to find out, what can you tell me thermodynamically? If you can find delta H, does that mean if it's endothermic or exothermic? Once I determine if it's endothermic or exothermic, where does heat go? How would increasing the temperature affect the net amount of product I'm able to obtain? So I'm going to give you a few minutes to work on these, and then we'll discuss some solutions.